Assalamualaikum warahmatullahi wabarakatuh. So this is the continuation of the power transmission line for the efficiency and regulation of transmission line. So in general, as you can see in this slide, phase voltage and current at sending end of the transmission line can be represented as this one. Okay, which is Vs. We have the magnitude and the angle, and also for the current source, the sending end current, which is you have the magnitude and also the angle. Similarly, at the receiving end, the phase voltage and current also can be represented like this. But please be reminded that we always use our voltage receiving end as our reference. So that's why we have zero angle here. Okay, and also we have the theta of the current, which is whether it is negative or positive. It depends on the type of load. The type of the impedance. But usually with this one will be negative because the impedance of the transmission line is always inductive type. Okay, and as mentioned before, in most cases, phase voltage at receiving end is taken as a reference, and that's why the angle for the PR is set to 0. And the total power, apparent power from the source, you can calculate by using this one, which is Vs and Is is the phase voltage and phase current. So for 3-phase, you need to multiply with 3. Okay, and this is Is. Please do not forget that Is you need to conjugate the Is, so it will become like this. Okay, so this is actually the complex power. Okay, sorry, this one I think it should be the complex power, total complex power, not apparent power, because the apparent power, this one. Okay, this is apparent power, and this one also, this is a complex power. Okay, so for the complex power received by the load, also you can use this equation. Okay, so this is also the apparent power. Okay, so as you can see here, the angle is negative theta I because the angle of the voltage of the receiving end is our reference, which is 0. And the real power magnitude delivered by the source and that received by the load, okay, can be written like this. Okay, so the real part of the complex power and then the real part of the complex power of the receiving end, you have like this. And since we have PS and PR, so P is actually referring to the real power of the sending end, and this is the real power of the receiving. Okay, so meaning that we can actually calculate what is the power losses inside the transmission line, which is you can just simply subtract the source power minus the receiving end power. Okay, like this. So the result here will be your total real power losses in the line. So from the losses, so we can actually calculate what we call the efficiency. So the efficiency of the transmission line is the ratio of the power received by the load, which is at the receiving end, to the power generated by the source. So if there is no losses, meaning that your efficiency will become 1 or 100%. Okay, and you can also calculate by using this one. Okay, output power over the input power. And sometimes the input power is not given, but if the power loss is given, so you can always also use output power plus power losses. Okay. So the voltage regulation, so similar with the transformer regulation, so it's actually referring to the degree of voltage rise at the receiving end of the line when a rated load, or known as a full load, is completely removed from the load terminal with sending end voltage is fixed. So we want to see whether the transmission line is has a good voltage regulation or not. Okay, so voltage regulations can be obtained by using this equation, which is the voltage at the receiving during no load minus the voltage received at the full load over the voltage received at full load. Usually the voltage received during no load will become higher, okay, compared to the full load, because when you are actually connected with a full load, the voltage usually uh, will be actually decreased compared to the when you have no load. So example of the voltage regulation, a very simple one. So the following result have obtained from the previous short line model. So we have the phase voltage and current at the load terminal like this, okay, and the voltage phase and current at the sending end. So this is actually a phase parameters, okay. And please be mentioned, this is a short line, so IR is equal to IS. Okay, because as you can see, the short line is like this, a very simple, which is this one is IS, this one is IR. So definitely IS is equal to IR. So the efficiency, so we can use, since this this value is actually a single phase value. So to calculate the efficiency, so you need to calculate the P total of the three phase of the receiving over the P3 phase at the sending. Okay, but since this is free, you can actually subtract this one. Okay, so and then you know that IR is equal to IS, so you can actually kill this one. So the remaining is a VR cos theta R over VS cos theta S. Okay, and from the previous examples, so your VR is actually 5773.5 multiplied with the cos of theta R 25.8. Okay, so this one is actually 0 minus theta I. Okay, where your theta I is actually negative 25.8. So that's why you have 0 positive 25.8, which is 25.8. Okay, and this is actually the angle, the cos of the theta V source minus theta I source, where your theta V source is 0.7 and your theta IS, which is equal to theta IR, which is negative 25.8. Okay, and then so the efficiency that you will obtain is around 98%. See, almost have a very low power losses. And the voltage regulations for that example is actually V based using the equation, which is a VR at no load minus VR at during the full load over the VR during the full load. Okay, and as you can see here, VR during the no load is equal to Vs. Why? Because when there is no load connected at the receiving end, the current is zero. So when there is a current, when there is no current, meaning that there is no voltage drop across the line. So meaning that Vs is equal to VR during no load is equal to the voltage source, which is 5916.6. Okay, and this is the voltage during the full load, which is 577.35. So you calculate and then you will receive that the voltage regulation is around 2.5%. So this is very small, and as you can see, there is no large difference from no load to full load. meaning that this power transmission line has a very good voltage regulation, meaning that the difference between during the no load and full load is very small. That is what we always want actually. So this is the example for to calculate the efficiency and also the regulation for the T circuit, which is this one referring to the medium. Okay, so this is example, the previous example. So we have calculated your VR and VS and also the IR and also IS. So as you can see, IR is 0 because for that example, the power factor is actually unity. Okay, meaning that the voltage and current at the receiving end is in phase. And the efficiency of the line, okay, so this one is actually three phase, so you just, but it's actually not different because you can actually cancel out the three here. And so you calculate VR IR cos theta. This one is actually referring to theta VR minus theta IR. Okay, so almost 0 here. So this one is actually 1 unity. And this one is VS IS cos theta S, which is this one is actually VS minus theta IS. Okay, which is 48.2 minus 3. Sorry, this one should be 3. Sorry, this one should be 3 minus 48.2 degrees. Should be like this. Okay, so the answer I think is correct, 97%. Okay, meaning that this transmission line is also very good, meaning that there is no losses. And what about the voltage regulation? So the voltage regulation, so we are using the same equation, which is VR during no load minus VR during full load over the VR during the full load. So to get VR during no load, so it's quite challenging for the medium length because okay, so because it involves a lot complex equation here like this. So this is actually the first equations that we derived for the medium T line, which is BS. BS is equal to 1 plus YZ over 2 VR plus Z plus 1 over 4 YZ square IR. And so from this one, since for the no load, meaning that IR is actually 0. So when IR is 0, so meaning that this is actually non-exist. Okay, so meaning that the voltage across the receiving end here is right now your VR no load. So your VR no load, you can calculate. So by transferring this one, so you will become 2 over 2 plus YZ multiply with the V source. So this is actually your voltage no load at the receiving end, which is you can calculate and then you will receive this answer. Okay, and then just use the magnitude. Okay, this is your VR no load, this is your VR full load. So from here you can see that the voltage regulation is around 2.3%. So this is a very small, and we can consider that this transmission line has a very good voltage regulator or regulation. Okay, so the same thing also you can see from this one. This is for the long line, which is not covered in our syllabus, but we can use this data to actually calculate the efficiency and also the no load. Okay, but and as you can see here, the voltage regulation is not good is around 24.7%. So meaning that the long line transmission has a very bad voltage regulation compared to the medium and also short line transmission. Okay, I think that's all, and we finish on the power transmission subtopic. Thank you very much for your attention.